Okay, I want to thank the organizers very much for the invitation to speak at this workshop. I'm very excited to be here, even if virtually so. I'm going to tell you about some joint work with my student, Chen Ma, and my collaborator, Yang Yu Lu. So the question that I want to talk about is, given an epidemic, how do we ensure it dies out in a reasonable time if we can maybe control how the various individuals in the population interact, or perhaps we can remove the individuals from the population. So in the case of humans, you can remove the individual from the population by, for example, giving them a vaccine. Animals are actually culled. And the where I see this fitting in within the framework of predicting and preventing epidemics is that you want to apply this to epidemics among animals. It's well known that many diseases among humans have a zoonotic origin, the most prominent example, of course, being COVID-19. And the question is, what happens when we discover an epidemic among animals that we think might have a chance of making a leap to human? We want to predict that this will not happen. And the key element of this prediction is making sure that epidemic dies out in a quick enough time frame. So right now, this is done using essentially very rough and brute force methods. If you've seen the news a few months ago, the Danish government had to call 17 million minks due to concerns that there was a version of the coronavirus spreading among minks that could make the leap perhaps back to humans. That, of course, cannot be the optimal thing to do. Really, you want to frame the question of how do you do all this? How do you restrict movement? How do you remove individuals from the population so that the epidemic will die out in a reasonable interval in the most economical way? So you want to put an upper limit on how much movement you restrict. You want to put an upper limit on how many individuals you remove from the population. And you want to be able to guarantee a certain rate at which the epidemic will die out. Okay, so I'm going to now discuss various ways to formalize this as a mathematical question. The methods that I'm going to use are going to be applicable to a wide variety of the epidemic models, from something very simple to something very complicated. So let me start with something that is very simple. We can start with the classic SIS model. You have the equation, you have a variable x representing the proportion of people who are infected in the population, and the derivative of x increases proportional to the product of x and 1 minus x. Uninfected people interact with infected people. And that's how the disease is spread, and there's a recovery rate, gamma. So individuals recover at a certain rate. And once they recover, they move back into the susceptible pool. Okay, so the SIS model is very simple. And in order to apply it to real world models, to things that happen in the real world, it helps to complicate it by making it more realistic in a number of ways. The first of which, the most natural of which, is to introduce a network in there. So not every infected person interacts with, it is not true that every infected person and every uninfected person interact, right? Really, the correct way to think about things is you have locations, and individuals are associated with a certain location. And they may meet individuals from different locations, from neighboring locations, and spread the epidemic, but they don't necessarily meet individuals located very far away. And so the way to do this, okay, I call this a network SIS model. Sometimes it's called a compartmental SIS model. You basically now have n variables, and the differential equation satisfied by the ith variable, xi dot, basically goes proportional to 1 minus xi, the fraction of people at location I who are not infected. And when that multiplies the variable xj, the proportion of infected people at location j, it gets multiplied by this coefficient aij. And this aij represents the network, okay? So basically, some of these aij's can be 0, corresponding to no interactions between individuals location I and j. Maybe some of these aij's are larger than others, corresponding to the fact neighboring nodes, for example, are going to interact more than non-neighboring nodes. And I see there's a slight typo here. It should be minus gamma xi, right? The minus gamma here is the recovery rate, and this is the differential equation governing xi, the proportion of infected at location I. Okay, so Of course, something like SIR and SCIR models are more commonly used to model, let's say, COVID-19. I want to actually talk about a more general class of models that contains SIR and SCIR as special cases and capture some of the intuition of what happens with a disease like COVID. But maybe COVID, maybe something else. This is kind of more general. So the idea is I'm going to have two classes of infected people. And in the context of COVID, you can think of S here as susceptible, E, the first class of infected people, roughly asymptomatic, X as symptomatic. And so you move out of susceptible, you move out of the susceptible group proportional to your interaction with either of the two groups. So E here is asymptomatic infected, X is symptomatic infected, but the coefficients beta 1 and beta 2 in front of these products are different because a symptomatic person, for example, may be more likely to infect someone upon meeting them. So once you move out of susceptible, you move into the E group. And so you see that here because the same two terms here appear with a plus sign. So the E group here is the asymptomatic group. From that, one of two things can happen. Either you recover at rate gamma 1, or you move into the symptomatic group at rate sigma. And so once you move out of E, you move into X. So X dot has the sigma E, and here you recover at rate gamma 2. So obviously, when you talk about COVID, it's very natural to come up with a model that has two classes of infected people. Of course, and by the way, this is not really original to this paper. There have been, it's most closely related to what we've seen in this preprint by Birch, Kandigan, and Feng. In a recent paper by Giordano et al., there were actually more categories because think about it, asymptomatic and symptomatic are very rough breakings. You can break each one up into different groups. For example, you can further break them up into whether they're hospitalized, whether they're quarantined, whether the infection has been diagnosed, and each of those groups potentially interacts slightly differently. So you can add more groups here, and everything that I'm describing is methodologically going to be applicable to those models as well. And of course, what you want to do, consistent with the spirit of what we're trying to do here, is to consider this over a network. So essentially, everywhere that you have a product of susceptible and infected, in a network model, you're going to have a product of Si and Ej, where every node now has three variables, Si, Ei, Xi, Si being the proportion of susceptible at that node, Ei being the proportional of asymptomatic infected at that node, Xi being the proportional of symptomatic infected in those nodes. So every product of Se gets replaced by a product of Si, Ej times Aij. And again, Aij are these coefficients that measure interaction between locations I and J. And everything else remains the same. Okay, so these are natural models of epidemic spread. So how are we going to affect how epidemics spread on a network? Okay, well, let's first talk about restrictions and how people interact with each other. And that basically means altering these coefficients Aij. And this actually forces us to take a step back and ask, how are these AIJs obtained? So we follow some earlier literature, again, the Birch, Kandigan, and Feng paper. We essentially take Aij to be the product, rather the sum, over all locations in the network K of tau ik, tau jk, where tau ik is the rate at which individuals from location I travel to location K. So the idea is, how do infections spread from location I to location J? Well, individuals from location I and location J have to meet somewhere. Where do they meet? Okay, you sum up over all the possible locations in your graph. Basically, and you get a product. You get this product tau ik, tau jk, and you sum all these things up, and there's a certain coefficient here that captures how disease spreads at that location. So you estimate these things from the real data. We actually do have data, for example, for humans, as I'll discuss shortly, measuring how humans travel from counties to counties. And you can actually create a graph whose locations are counties and estimate these things from the data. Okay, but how do we control, what control do we have over how people move? Well, essentially, we take a simple model where each term in the sum gets multiplied by some zk, which is between 0 and 1. So zk equals 0 means you shut down everything in that node. Zk equals 1 means you don't shut down anything in that node. How does this happen? Well, for example, when you do something like you put a restriction on density, you limit how many people can be inside a store. What you're actually going to do is you're going to make things less transmissible. So you're going to multiply this beta k by some factor. You can also do something similar in terms of saying that when you shut down places in a county, when you shut down nightclubs, when you shut down restaurants, you're also affecting travel rates. And so that also will result in fewer trips, all of which you incorporate into this factor zk. So that gives us a model for how we can affect things. Essentially, we multiply the mixing at every location by this coefficient zk between 0 and 1. And then what is the cost associated with this? Obviously, we want to try to control this process by shutting down as little as possible. Well, you can take a number of models. I'm going to just stick to one in this presentation, but this is not the only model you can take. So you want something where zk equals 1 corresponds to doing nothing, has a cost of 0. And when zk is 0, that means shutting down everything. And since we're going to apply this to something like counties in the United States, you don't want to shut down a county 100%. So the idea is that we take something like, we take a cost that's proportional to 1 over zi, so that it blows up as zi goes to 0, but it's some constant which we offset here to be 0 at zi equals 1. Okay, and then that's the cost of the action we take. And what is our goal? Okay, so for the SIS goal, for the SIS network model, we want to send the epidemic to 0 at a certain pre-specified rate. For the COVID-19 model, the objective has to be slightly different because the epidemic for sort of SIR type epidemics, like the model we've given, the proportion of infected people are going to go to 0 either way. It's only a question of, is it going to go to 0 because because the disease burns through the population, or because every individual infects fewer than one others on average. So we're going to ask to guarantee that the reproduction ratio is always upper bounded by something. In this case, you can write down the reproduction ratio as the related to the largest eigenvalue of a certain matrix. And since we're working in continuous time, we're going to have the log of that be upper bounded by some negative number, negative alpha. And the alpha is what we're going to be referring to as the rate. Okay, so now this basically defines a problem the problem is now well defined. You have an epidemic model, you have a goal, you have an action you can take, and you have a way to measure the cost of an action. So now we can ask, given a rate alpha that you want to achieve, what is the minimal, the cheapest, let's say, lockdown to force that, to achieve that alpha? And the main theoretical result behind the work that I'm presenting you is that you can solve this problem quite efficiently. So under a certain condition, which we call the high growth condition, the final result here is you can do it in essentially linear time. Okay, so the notation here is O tilde, which basically the tilde hides some log factors, which are not shown here. The problem is specified by the entries of the matrix A, which tells you how the various nodes of a network interact, as well as the various other coefficients like the betas and gammas. And the time it takes to compute the optimal solution under this high growth condition, which is satisfied for the models that we estimate of COVID, is proportional to the number of non-zero entries in A times this parameter kappa, which is the imbalance of the optimal shutdown. So the imbalance of a shutdown is the ratio of the largest and smallest ZIs. That's the definition of kappa. So this is the complexity of computing the optimal shutdown to achieve this rate alpha. And we also show you can always do it in an O(n) cube time. Okay, and previous work basically did this using convex optimization and primal dual, or by solving it as a nonlinear optimal control problem, all of which are much, much less scalable than the methods we propose here. So basically, when you have an algorithm that works in essentially linear time, you can scale that up to very large systems. So this is our result. Once we obtained it, we tried to apply it to real data. We got some interesting and most importantly, very counterintuitive results that I want to tell you about. So we used it in a model of the epidemic in New York State. We used existing parameters for COVID-19 spread. We also used existing parameters for SIR spread. And we also considered what an SIS epidemic would look like with the same parameters. And we found that when you look for an optimal shutdown, guaranteeing a certain rate, you get a result that's quite heterogeneous. So here, for example, is the counties of New York State. The color represents the strength of the shutdown in each county. We're dealing with these ZIs between 0 and 1, which roughly correspond to how strongly you want to shut things down. So in some cases, these ZIs are basically 10%. You want to multiply everything by 0.1 in that location. And in other locations, it's more like 70%. So the optimal lockdown is quite heterogeneous. Not only that, but you get a benefit from that heterogeneity. So in this graph, compare the red and the orange. The red is our optimal lockdown, and the orange is the best uniform lockdown, same across all counties, found through line search. And you see that indeed, this highly heterogeneous structure does give you benefits. So in every case, we outperform in terms of the number of cases. And in the SIS case, the difference is particularly stark. Okay. Now, you might wonder, what does it actually do? Uh, you might make a guess, that is to say, the optimal shutdown. What does it look like on a graph? You might make a guess that it basically will shut down the more central places in the graph harder. Surprisingly, we find that this is either untrue or only partially true. So here is an experiment on synthetic data. We generated a geometric random graph. In a geometric random graph, you throw a whole bunch of points in the unit square and you connect every point to neighbors. That's a geometric random graph. This is the first figure, and it's also the third figure over here with slightly different parameters. The degree in a geometric random graph is going to be quite heterogeneous, even though there's a certain symmetry. Every point is treated the same in a way, but just because of the inherent randomness, you will have a substantial, maybe a factor of 4 difference between the degrees here. This is 200 nodes. And yet, even though there's a factor of 4 difference, there's barely any difference in terms of the optimal shutdown. There's a very slight negative slope, but if you look at the range of the y-axis, this is these ZIs, the strength of the shutdown, they vary between something like 0.12 to 0.14. So basically, a factor of 4 difference has almost no effect. Now, you can make centrality have an effect by throwing something we call a hotspot. So a hotspot's basically connected to some constant fraction of the nodes in the network. So think of a hotspot as something like an airport. Everybody connects to it. And yeah, when we do that, we do find, here's a graph with 4 hotspots. We do find that these hotspots, which are connected to a constant fraction of the nodes, so the difference in degrees are huge, you do see them being shut down harder. But something like, merely a factor of 4 difference in the graph has barely any effect. So the connection between centrality, and the same thing is true, by the way, if you replace degree by something like eigenvector centrality. So the lesson here is that the connection between centrality and how hard the optimal shutdown really locks down a place is very nonlinear and unintuitive. We noticed something else about our optimal lockdowns. So when we applied our data to New York State, using data from April 1st, we found that you actually shut down New York City a lot less, right? So the higher numbers here correspond to looser shutdowns. You shut down New York City a lot less than everything else upstate, even though using data from April 1st here, which we're doing, at that point, New York City had the vast majority of the infections, something like three-fourths, I believe. So somehow it shuts down places with fewer infections, which is, again, very strange. We thought maybe there was, our first reaction is to think maybe there was a bug in code, maybe something's wrong with the data. So what we did is we compared our shutdown, which is in red, to the homogeneous shutdown of the same cost, which is in orange, two, we searched over all shutdowns of New York State, which have two parameters: how hard you shut down New York City and how hard you shut down the outside of New York City, everything else. And you shut down New York City harder, and that's in blue. So our shutdown outperforms. So you really do get a benefit from shutting down, in this particular case, at least, of shutting down places that have fewer infections. And again, this is very counterintuitive. It does not always happen. In some cases, it does not happen, but it certainly does happen if we if we use a model of New York State for April 1st, and we ask for here 2% daily decay. That's the rate that we're trying to achieve. So this is counterintuitive. It does not seem to be widely realized. So the implication is that it's very natural to use the heuristic of how hard should you shut down places, shut down the places with the most infections, right? But sometimes that is the very opposite of what you should do if your goal is to drive the disease to zero at lowest cost at a certain rate. And this point does not seem to be widely understood. Okay, so I want to kind of finish by telling you about some preliminary work here about removing individuals from the population. Again, this is maybe closely connected to what happens if you have an epidemic among animals that you don't want to leap to humans. It also can be easily applied with some small modifications to the problems of vaccine allocation. And indeed, that is how we apply it. So in mathematical terms, you have the exact same models that we had before. You have models of either SIS or you have models of COVID-19 over a graph. Actually, all the charts I'll show you are for COVID-19. But what you can now affect, you can't affect the travel rates, but what you can affect is you can remove people from the susceptible population. So you just subtract some vector delta. And you have some budget, okay? So you can only subtract B total individuals. That's how many vaccines you have. And the question is, who do you give that to? So under some assumptions that are satisfied in the data sets that we're looking at, something on the positive definiteness of certain matrices you construct from the data, we have been able to show that you can solve this problem by solving a semi-definite problem plus a line search. So it's not as scalable as the problems I described a little bit earlier, but you can still solve it. And once you do, you find some results that are also intriguing and counterintuitive. So for example, let's apply it again to the model of New York State. And here I'm going to show you several different things. So this black curve corresponds to no vaccine. The blue curve corresponds to giving vaccines to counties in New York State proportional to infections. Orange corresponds to giving vaccines to counties proportional to their population. And what our methods found is in red. So you see they're better on all parameters. So you get a little bit of savings, maybe 5% or so here in terms of number of deaths, maybe 5% or so in terms of the number of cases. But the epidemic actually dies out substantially quicker. Note the x-axis here is log scale. So you can do something that's non-trivial. And when I say it's non-trivial, what I mean is this. This is what our method does, right? It assigns, the color here codes the proportion of the population that gets the vaccine in every county. You can compare it to what happens when you give the same proportion to everybody, or when you give it proportional to the number of infections. Here, you would give more to the various locations in the sort of New York City area. So these kind of make intuitive sense. This does not really make intuitive sense, and yet it outperforms them. Okay, another thing you can do, and this is, I find these results quite intriguing, is you can also add demographics in there. So the previous chart I showed you was just allocating vaccines to counties, but now you break every county by population demographics, by age group rather, is what I mean to say. So you break it into age groups like 0 to 4, 5 to 19, 20 to 29, 30 to 44. So you have 62 counties, and in every county you have 1, 2, 3, 4, 5, 6 subpopulations when you break them down by age. And so then the question is, how do you allocate it, not just by location, but by location plus population? So you can apply our methods to this problem, and you're going to get something which basically has as good of a death rate as just giving it to, as any of the other methods, including just giving it all the vaccines to seniors, but has substantially fewer cases and dies out much quicker. And it achieves it by doing something very weird, by basically giving 100% of the vaccine to the 30 to 44 group. Again, this is not easy to explain, and it's not necessarily a very intuitive result. All that can be said is somehow by doing something, by using strategies that mix location and age group, you're targeting it at some key points in the graph, which governs the infection spread, and somehow giving it to these nodes, they have more important locations in that graph. So I'm not necessarily saying this is the optimal thing to do. In fact, this is the optimal thing to do using these metrics for one particular budget of how much vaccines you have. The patterns will change depending on, let's say, how much of the blue you have, how many vaccines you have. Still, this is an interesting pattern that does seem quite counterintuitive and is not widely discussed. Okay, so in conclusion, I want to say you can, some of the results I've presented, specifically all the stuff that deals with lockdowns and on the archive, our major contribution here has been methodological. We've developed new algorithms for both, for stabilizing epidemics, either by removing individuals from the population or by affecting how people can travel. And sort of the major lesson is that that I'm drawing from this is that once you run these algorithms, you obtain conclusions that, from the point of view of network science, are very counterintuitive. I mentioned some of these counterintuitive conclusions here. We should not, nevertheless, lose track that this is based on the available data, and the available data has a lot of blind spots. Okay, so for example, all these results are based on data for how much people from counties in New York interact from each other. And it's based on a certain service called SafeGraph. And SafeGraph data SafeGraph is based on pinging people's cell phones and seeing where they're located. And it doesn't tell us, for example, whether the individuals in question are located in a car and alone with no possibility for transmission, or whether they're in a restaurant, or whether they're walking down the street. We just get, all the data we have is based on minutes spent outside the home, minutes spent in each neighboring county. So we constructed a model based on that, and we applied these results, and we got some intriguing and counterintuitive stuff. But I would not necessarily say that this is what we should be doing. Rather, the punchline here is maybe that for the next pandemic, it would be great to collect very precise data on average, how people travel from county to county. And then the kind of algorithms that we have developed here can be applied. Because as you can see, you can get these counterintuitive phenomena. The best thing to do in these situations, in terms of either vaccine allocation or lockdowns, may be something that is that's not easily guessable. And we do need the kind of algorithms that I'm talking about to find them. And with that, I'm going to thank you for your attention. And if I can find the stop recording button, I'm going to click it.